Many of these videos were recorded during the summer of 2020 when we were using Python 3.7. Now in 2024, we are using Python 3.11 with Anaconda 2024.02. There are very few differences between Python 3.7 through 11, at least at the level of this course. I have updated the lecture slides, but I have not bothered to update the lecture videos unless there is some actual difference between Python 3.11 and 7. So when a slide mentions Python 3.7 or Anaconda 2020.02, please be aware that what we're talking about is also true of the current versions of Python and Anaconda.
All right, welcome to Carnegie Mellon University's
Introduction to Python course.
This will be the first lecture of week 1. There's going to be 4 lectures each week of roughly half an hour to 40 minutes each. So let us begin. Well, what about Python? Python is what's called a multi-paradigm programming language. That is, you can use it to do top-down functional decomposition kinds of programs, which works very well for small to medium-sized programs. You can also use it to do object-oriented programming, which works better for larger programs and also is a better mechanism for reusing code in the future. One of Python's big advantages is that it's quite easy to write, certainly in comparison with more traditional compiled programming languages like the C, C++, and Java languages, and it's therefore great for rapid software development. Roughly speaking, estimates are that especially junior programmers can write a given amount of functionality in Python about 3 times as quickly as they can do the equivalent amount of functionality in C++ or Java. Python is an interpreted language. That is, the lines of code that you type are interpreted on the fly as you type them in or as a script that you've written is executed. And consequently, this makes Python programs inherently slower than programs written in C, C++, and Java that do equivalent things. But although efficiency is very important in programming, there's a trade-off between the efficiency of the programmer versus the efficiency of the finished program. If you have a program that you only need to run periodically and that is not creating a bottleneck, then in many cases, if not the majority of cases, it's more important that the programmer be able to get the program working correctly fast as opposed to the program itself running fast once it's been written. And because Python is such an efficient language to write code in, it's become very, very popular in the last handful of years. Now, just as an aside, the Python language is named after the Monty Python British comedy troupe, not after the snake, although if you look at Python documentation, you'll see it does have typically a cute little snake icon on the documentation.
Python is an open source project, meaning it's free to use for personal use or academic use or what have you. It was originated by a fellow named Guido van Rossum, who was the driving force behind Python for many years. Nowadays, an organization sort of loosely knit in the way of open source projects, this organization called the Python Software Foundation controls Python, and they have new releases on a periodic basis. And in the so-called Python ecosystem, there are a tremendous number of modules developed for free by people in the so-called Python community. Now, we are going to be using, in this course, a version of Python called 3.11. And in particular, we're going to be installing a package called Anaconda version 2023.07. So it was released in July of this year. You can obtain this Anaconda from anaconda.com. And you can take a look at my installation video about how to go about doing that. Now, anaconda.com is happy to sell you stuff, support and so on. But for our purposes, since we're just using it for a class, we don't need to actually buy anything. And as I said, when you take a look at my installation video, you'll see how to go about setting it up. Anaconda is not merely Python. Anaconda incorporates a whole bunch of so-called Python shells or interpreters that process the Python language, excuse me, and it also includes a whole lot of more sophisticated so-called integrated development environments, which give you a text editor that you can type Python code into, and then a so-called command window or shell window in which you can execute the Python code that you've typed. Okay, so these integrated development environments are generally referred to as IDEs. In addition to these shells or interpreters and these IDEs, Anaconda also comes with a tremendous number of additional modules, including NumPy, which we will have time to get to toward the end of our class, as well as pandas, matplotlib, and tons of others that are beyond our scope.
Interacting with an Anaconda development environment. The simplest integrated development environment for Python is this thing called IDLE. Okay, IDE stands for Integrated Development Environment, and IDLE is an integrated development environment that's very simple that comes as part of Python itself. When you click on the Start button, or you can also execute this from within Anaconda Navigator if you are using some system other than Windows. I happen to be using Windows, so I'm going to click the Start button, which you can't actually see that in this recording, but here's the upper part of the Start menu, and I do have an Anaconda prompt in my Start menu, which I will click. And what that does for me is to launch a command.com style command interface that's aware of my Anaconda environment. In that environment, I'm going to type, IDLE to start the IDLE development environment. Okay, here's the environment, which fires up in wherever it feels like it on the screen. And I'm going to change its size and position to put it where I want it. Okay, so here we are. I now have my Python shell running. The shell is able to receive and interpret Python code. Okay, now a shell for Python is a little bit like a shell for an operating system, such as the bash shell for Linux or the command.com command interpreter on Windows. But the Python shell executes Python code rather than operating system level commands. The three greater than symbols that we see here, that is the shell's prompt, waiting for me to type some Python code. Okay, so if I just type a number at the prompt, the Python shell's default behavior is to simply repeat back to me what that number is. If I do a computation, let's say, like 7 divided by 3, then the Python shell's behavior is to perform that computation and to display to me the result of that computation. So 7/3 is 2 1/3. So the representation that's being displayed here is 2.333333, etc. If I want to get out of my Python shell, I use the command, or the function actually, quit. And here is what I consider a sort of both amusing and annoying thing about Python. If I type quit and hit the enter key, it knows what I'm trying to do. It knows that I'm trying to get out of the shell, but it says, no, 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 you have to use quit with parentheses or press Control Z. I'm going to ignore the Control Z. So I'll type quit with parentheses to make Python happy, to make the shell happy about my syntax. And when I hit the enter key now, I get this little confirmation window asking me if I really want to kill the shell. So I could click OK at this point, and that would get me out of the shell, out of the Python shell, back to the Anaconda prompt shell. But because it's so annoying every time I start this idle interface to set its size correctly, I'm just going to cancel this instead and remain in the shell. All right. Now, in Python code, it's a good idea to write comments about what your code is supposed to be doing. And a comment consists of a pound sign or sharp sign or tic-tac-toe board or hash mark or whatever you want to call that thing to the end of the current line. Okay, so when the shell sees, when the interpreter sees a comment that is anything from a pound sign all the way to the end of the line, that is simply ignored. Nothing is done with that at all, other than that it's thrown away. So that all in it of itself is not very useful, but I might, in a program that I have stored in a file, say something like A gets 123, and then comment that A is a variable, and I might say X gets 2.7, and then comment that X is a variable. Now, these comments also are not really very beneficial. It would be more useful for me to say what this value 123 stored into A actually means. But this is illustrating the idea of commenting code. And this part of the code, A gets 123 and X gets 2.7, that is what's called an assignment. And what it does is to create a variable and cause that variable to refer to the value on the right-hand side of the assignment operator. So I now have a variable named A referring to this integer value 123, and I have a variable named X referring to what's called a floating point value 2.7. I can see the value of A by just typing its name, because the default behavior for the Python shell is to evaluate whatever you type at it and display the result. So it evaluates A and tells me, oh, well, A is referring to 123. And likewise, if I type X, the shell says, oh, X is referring to 2.7. So A and X are legal variable names. Let's talk about the actual rules for what constitutes a legal variable within a Python program. The first character in a legal variable name has to be either a letter or an underscore. Now, the letter can be, or a letter I should say, can be either uppercase or lowercase. And in fact, upper and lowercase letters are distinct. This is an important thing to bear in mind. So if I say A gets 3 with a capital A, I have now created a variable named capital A, which is distinct from the little a variable that I had previously created. All right, so if I just type a in lowercase, that variable, a in lowercase, little a if you will, is still referring to 123, whereas a uppercase is referring to 3. Now, if I say 3 gets something, 3 gets a in this particular case, this is not legal because 3 is neither a letter nor an underscore. And it's a good thing, actually, that I can't modify the integer value 3 to be something other than 3. Okay, so that's it's good that that is going to give me an error. Okay, now if I say underscore 3 on the other hand, in that case the first character is a letter or an underscore, and following that initial letter or underscore I can have 0 or more. There we go. All right, got my highlighting under control there. So following that initial letter or underscore, I can have 0 more characters, which are either letters, decimal digits between 0 and 9, and or underscores. All right, so underscore 3 is a legal variable name in Python. And now when I access underscore 3, I'm going to get back the value 9 that that variable refers to. So underscore 3 is a legal variable name. It's probably also a stupid variable name. It's probably not very wise to define variables with names like underscore 3. One of the places where underscores are most commonly used, actually, is to separate parts of a multi-word variable name. So if I say has an apples with a couple of underscores, then it's easy to read has an apples, and the number of apples that I have is going to be 12 here. All right, so has an apples refers to 12, and that's easier to read than has an apples. That looks like has an apples. Okay, so the underscore is often used to create meaningful variable names consisting of multiple words to separate the words or the components of the variable name from each other. Because upper and lowercase letters are distinct, if I create a variable named AA, referring to 2, both of those A's are in lowercase, and then I create little a, big A gets 3, big A, little a gets 4, big A gets 5, these are 4 completely independent variables, and the shell, the interactive Python shell, has no trouble keeping track of these things. AA in lowercase is referring to 2, little a capital A is referring to 3, big A little a is 4, big A is 5. So these are legal, but probably also dumb. It's probably stupid to create 4 variables whose names are very similar to each other except for letter case. All right. So I recommend always choosing a meaningful variable name, using underscores to separate the words or the abbreviations, if you will, in that variable name. For example, it turns out that by definition, an inch is defined to be the same length as 2.54 centimeters. So centimeters per inch is 2.54 by definition. Okay, the meter is defined in terms of some kind of physical constant. Inches are defined in terms of meters, or in this case, centimeters. So it's easier to think about 2.54 centimeters rather than 0.0254 meters. In any case, that is a legal variable name whose name makes sense that I can use later in my code to remind myself how many centimeters there are per inch. Other programming languages have other rules about what you can legally name variables. For example, in the R language, if I wanted to keep track of the number of siblings that I have, I could use a dot in the variable name in the same way that I have so far used the underscore. Now, this would work fine in R, but Python doesn't understand using dot in a variable name, so Python is going to yell at me. Python treats the dot to mean to look up a certain member of an object, which gets us into the realm of object-oriented programming, which we're not to yet. All right, so I cannot use a dot in a variable name in Python. Likewise, if you're used to using dashes in English documents to separate words, that's not going to be legal in Python. Python uses the dash symbol in this context as subtraction. And so Python thinks I'm trying to say cm minus per minus ft, and there are no variables whose names are cm, per, and ft, so that causes confusion. And then doing an assignment operation to the result of a computation is also confusing to Python. So I get an error message from this kind of thing. All right, so in summary, if you want to create a legal variable name, the very first character has to be either a letter or an underscore. And recall that uppercase letters and lowercase letters are distinct. If the variable name is longer than one character, then subsequent characters can be either letters, upper or lowercase, or digits between 0 and 9, or underscore characters, any mixture of those that you want. But any other kinds of characters that you use on a variable name will result in an illegal variable name. Okay. Well, so one thing that you can do with a Python shell that's almost the most trivial thing that you can do with it is to just use it as though it were a calculator. We have in Python the usual arithmetic plus, minus, times, and divides operators. That is addition, subtraction, multiplication, and division. And as you're used to doing in pencil and paper mathematics, the multiplication and division have higher precedence than addition and subtraction do. So using these operators, if I say 3 plus 7 times 2, well, the times operation, the multiply operation, has higher precedence than the add operation, the addition. So this is going to be evaluated as 7 times 2 is 14, and then 3 plus 14 is going to give me 17, so that will be my result. If I say something like 3 times 2 minus 1 over 5, again, the multiplication and the division have higher precedence than the subtraction. So I'm going to compute 3 times 2, which will give me a 6. I'm also going to compute 1 over 5, which will give me a 0.2 value. Then I'm going to compute the difference of 6 minus 0.2 to end up with a result of 5.8. Okay, so this is the same as what you can do with the the Windows calculator or the calculator that you have in your pocket if you still have an ancient calculator that you carry around, or on your Mac or whatever. You can use parentheses to override precedence. It's also important to understand that the associativity, that is the order of grouping of these operators, is from left to right. So if I say something like 2 plus 5 minus 4, that's evaluated as though it were 2 plus 5 quantity minus 4. That is, the addition and subtraction are evaluated from left to right. In fact, in the case of this addition and subtraction, it's irrelevant which order I evaluate these things in. 2 plus the quantity 5 minus 4 is 3. 2 plus 5 quantity is 7 minus 4 is also 3. So although the associativity rules exist, they don't really affect anything for this particular example. If I say, on the other hand, 2 plus, and then well, I was going to say 2 plus 5 minus 4 in parentheses, but I just got done telling you that that's the same thing. So that's a dumb example, but it is the same thing. Let's take a look at this thing on slide 11 here, though. If I have 8 minus 4 plus 2, well, 8 minus 4 is a 4, plus 2 is a 6. That is quite different from 8 minus the quantity 4 plus 2. Okay, so if I use parentheses to force the addition to be performed prior to the subtraction, then I'm going to get 8 minus 6, which is 2. All right, so you can use the parentheses to override either the precedence and or the associativity of these arithmetic operators. Now, if you have a complex calculation that you're trying to perform, then it's a really good idea to use variables to imply to the person reading your code what the meaning of all these numbers is. For example, here I have 5 over 9 times the quantity 80 minus 32. And I have an answer. Now, this just looks like some random arithmetic expression that I plucked out of thin air. But in fact, this computation is doing a useful thing. This computation takes a Fahrenheit temperature, which is 80 in this particular case, and converts that into a Celsius temperature. If you take a Fahrenheit temperature and subtract 32, and you then multiply the result of that subtraction by 5/9, the number you get out is the Celsius equivalent. Okay, so 80 degrees Fahrenheit here is equivalent to 26.6666 degrees Celsius. I can make this more clear to someone looking at my code by saying Fahrenheit gets 80. I'm too lazy to type Fahrenheit out, and I probably can't spell it right. So I'm going to say Fair is 80, and then I can say Celsius, again, rather than typing out Celsius, is 5/9 of, or times, the Fahrenheit temperature minus 32. Okay, I made a typo there. So this should be 5/9, not 5/0. All right, so 5/9 of the Fahrenheit temperature minus 32. And so my Celsius temperature is 26.6666. Okay, well, so that gets us to the conclusion of this first of 4 lectures for week 1. We've introduced the ideas of the shell, numbers, computations involving arithmetic operations, variables, and assignment operations. and you are invited to try a little lab that we have, Lab 1.1, that will give you some practice with the material that we've discussed in this lecture. Okay, so have a look at that if you would like, and we will connect up again with Week 1, Lecture 2.